Great, recording is rolling. So welcome everybody to back to physics. Today is Tuesday, November 16th, and uh, Monday, Tuesday, Wednesday, which we're in the middle of. I'm in the middle of the story, so I'm telling you guys a bunch of rotational dynamics topics. And yesterday I got to about here-ish. So also I'm making one video for AP and honor. So AP, this is your guys's next puzzle problems from your book, and also you guys have AP Classroom for my honors classes. Honors classes have this fun stuff going on off this page. Okay. Now we're not actually going to get to these problems for a long time because at the end of this week is Thanksgiving break, which is a whole week, which is going to be really nice. I'm definitely going to use that time, so we won't even touch these until after that. But just so you know, there you go. Okay. Let me recap the story from yesterday. We'll lead through what we went through. So talked about rotational kinematics, so kinematic motion. Say if you're watching this disc, say spin to a stop, you know how far it spins, how much time it comes to a stop. You can use these three values. You can use these kinematic formulas to calculate the initial spin rate and also the rate that's slowing down. Okay? That's that. We also did. There's the math for that, the equations. Okay? We also did a graph interpretation of that. So omega versus t, which is a really rich graph because the area under the curve tells you how far it spins, and the slope tells you the rate it was slowing down. Okay? We looked at centripetal force, which we've actually done before. So by the AP's book, this is unit 3. You guys did a whole lab on this. So this Play-Doh canister of some mass moving in a circle of this radial size at this speed, what force would hold that in balance? You guys figured out yourselves a few weeks back that force is equal to mv squared divided by r. But you know what? That v is a linear uh, uh, point of view. What if you wanted something like omega, like a spin rate, radians per second? Well, pop in this, do the substitution, you can get this other expression. It's also m times omega squared times r, which is a more handy expression for some applications. If you have like a solid, like rigid disk spinning, or like O'Neill cylinder, which you guys will see at the end of this week, sometimes it's easier application. Did a little bit of math on that. Right, then I started introducing new ideas. And first of these new ideas was something called rotational inertia. So you guys know inertia is the resistance to change in motion. And up to last week, it was only represented by the mass of something. The more massive something is, the less it wants to change its motion. Put a force on it, the less it will accelerate for more mass. But yesterday, I said, well, it's not just how massive is something anymore. It's also the location of that mass. So like this turntable, if I put this mass in the middle, turntable, okay, so it doesn't take a lot of effort to get going. But if I slide this out here, well, now for the same angular rotation, this has to move a long distance. So, there's a lot more inertia associated with that. Right? It's really hard to get that spinning. Right? We looked at a few examples of balancing a pin on your finger, nearly impossible. Balancing a meter stick, really easy. Why? Has so much more rotational inertia. Right? MR squared for a single point. Some of them are squared for like a whole like rotating object. Hold on. Time out here. Can I mute this? Okay, so back here, looked at sky tightrope walking, bike wheels, this sort of thing. But you know what I totally forgot to mention yesterday is one of my very classic rotational inertia demos. So let's take a look at this. I've got a couple of meter sticks up here. I'm going to pull this out so you guys can see this, but I'm going to draw this first for the video. Okay. Got a couple of meter sticks. And they have some weights taped to them, but at different locations. So one of them has weights taped to the center. Actually, I should call this M and M, and each mass is like 500 grams, like this guy right here, 500 grams. And the other one has masses taped way the heck out on the ends, like here and here, M and M. Okay. And question is, if you grab the meter stick right at the middle and start shaking this back and forth, so same one here because we're going to compare these two. Shake this guy back and forth. do those feel different? And which one is easier to rotate back and forth like this? So let me grab these two so you guys can see them in person in classroom. Okay. So you guys see this? Now, at the base of it, these might look really similar. Like they have the same mass total, they have the same weight. If I launch these like javelins, same force, they accelerate the same, they move the same. Like, everything's the same, right? Until you start rotating these things. Now, I want to see show of hands before I actually do this. Which one of these is actually going to be easier to shake back and forth? Is it going to be the one where they're really close together, or is it going to be the one where they're really far apart? Let's see, show of hands. How many guys think the one where they're really close together is going to be easier? Ooh, who says where they're far apart is going to be easier? Okay, so let's see. Okay. The one where they're close together. That's what that one looks like. Here's the one where they're far apart. Oh man, really hard to change state of motion. Right, this one really easy. This one really hard. And look at it in the context of this rotational inertia. Remember I told you it was mr squared for a single point? It's got m times a little r squared, plus m times a little r squared. For this one, got same mass times a big ol' r squared. Oh boy, this one has a lot of rotational inertia. Really hard to get it going. And once it is going, really hard to stop it and change it. So I will pass this around. You guys can feel this yourselves if you want to. So back to the, what's here? Okay. It is said as, you guys remember that I is equal to, well, for a single point, it's mr squared. And for some general shape, it could be like the sum of, so in this case, if I ignore the meter stick, which also has a little bit, and just focus on these masses, here's a little tiny r, so this mr squared plus this mr squared, I'm adding them together, that's what the segment is, like sum of. Versus this bottom picture, we got big ol' r, right? This mr squared plus mr squared. Whew, that's a big old difference, right? This bottom one has a lot of rotational inertia. Really hard to shake it back and forth, or change the state of motion. Okay. Yeah.
Does this have any relation to that thing where like figure skaters do, where it's like if they put their arms inside, they spin faster?
Yeah, you guys hear Ryan where you guys have seen figure skaters, right? They go into spin, they pull their arms in and spin faster. This is related to that. Because they would be changing, if they pull their arms in, they're going from the shape to the shape. Okay? This is related to that. That's actually angular momentum, which I'm going to talk about tomorrow. Yeah, so that is a sneak peek into tomorrow. So yeah, good thing ahead there. Okay. So it's rotational inertia. Told you guys about parallel axis theorem, which I don't think AP cares about, but that could show up at college. Okay. Right, then we started talking about torque. Right, so there's a few perspectives on torque, but a really good entry point is that torque is just R cross F. So classic example, opening a door has some width, you put a force on the door handle, and then it'll rotate about the door hinge, right? Create this turning moment called the torque. Okay? Now, remember this is a cross product, so only the perpendicular components matter. That's why you want to push 90 degrees to the door. See, if you push in the same direction as the width of the door, it's not going to turn the door, right? So you want 90 degrees to maximize the torque. Maximize your force. Also maximize that radial distance. See if the door handle was close to the hinges, it'd be really hard to open the door too, right? Okay. You know what else torque is also equal to is I times alpha. Right? So not only is torque R cross F, torque is also I times alpha. And this is analogous to Newton's second law of motion. That's why I wrote Newton's second law of motion here. What this is to linear motion, this is to rotational motion. See, like M is now I, A is now alpha. Okay? And force, well, that's kind of analogous to torque. Think of it that way. Okay? So you guys see this disc down here? Say I put a force at some radial to spin this disc. Did I solve this with you guys yesterday? Or I think it's about as far as we got. Right? Hold on to that idea because we're going to solve that. But right before we do, I've got another demo for you guys. So hang on to that idea. We'll solve that in a minute. Okay. I've got a question for you guys involving this here spool. All right. So do you guys see like an inside radius and an outside radius? In the inside radius, see I've got this string winding around, going all the way around this thing. Okay, that's it. Okay. And so let's get a cross-section view of this. See this from the side. Here's the ground. Here's my spool. Oh, that's the outside radius. Here's like the inside radius. Okay. And the string's round. Okay. Now, what if I pull on that string? Let's say just pull straight up. apply a force that way. Okay. Question is, which way is this thing going to rotate? Is it going to rotate counterclockwise to the left or clockwise to the right? Okay. So this is not a trick question. Let me say show of hands anyway. Okay. How many guys say counterclockwise to the left? Counterclockwise to the left. Okay. Does anybody say clockwise to the right? Let's check it out. Let's do the science. Okay. So pop this down here, pull straight up, and oh, it does go counterclockwise to the left. Okay, so no surprise, right? That's all fine, good. All right. What if I do this? What if I pull straight to the right? That way. Okay. Now this one might be a little trickier to think about. This one tricks up a lot of students. Okay. Now, if I pull to the right, is this thing going to go still counterclockwise to the left, or is it now going to turn clockwise to the right? Let's see, show of hands. How am I going to say this is going to rotate counterclockwise to the left? And who says it's going to go clockwise to the right? Who says that? Okay, well, let's do the science. Do the science. Okay. So pop this down here, string, and pull to the right, and oh, it does go clockwise to the right. They see it goes clockwise to the right. Okay. So if I pull a different angle, actually reverse direction. This one's to the left, this one's to the right. Okay. Now, if you thought it was going to rotate counterclockwise to the left, then you may have been thinking, well, I know that torque is R cross F. And you may have been thinking maybe it would like pivot about this point, something like that. That's not actually the point that it's pivoting about. It's actually pivoting about this point down here. And that's only important from a physics point of view because there's friction at this point. And friction would be opposing that motion. So you got like a friction force on the other way. Okay. Here's your actual radial arm between those two forces. Call this R. So I bet you see it now, right? But this were like your door. This is like the door hinges, right? Where there's a friction force down here. Okay. If it weren't for that friction, this actually would not rotate. It would just like, well, maybe a little bit because of inertia, but it would just like pull to the right. This friction actually allows it to like start rolling like that, right? Okay. So hey, if I pull it this way, here would have been the radial distance from that point of view, right? That was the original pull. That's why it goes off counterclockwise. And this one, here's the radial arm, so that's why it goes clockwise. Do you think that there's some angle I could pull at where all that torque cancels out, where it goes, not left, not right, but maybe it cancels out somewhere? And what angle would that be? Oh, well, you know what? I remember that if I push straight into or away from the hinges of a door, that would cause the door to not rotate. So maybe if I treat this point down here as like the hinge point, could maybe if I pull like in that direction, right? So I thought this was sort of related to also is if you see a car rolling down the road, this is kind of like a tire, right? Whatever the speed of the car is, let's say the speed of the car is like 60 miles an hour. Right? The middle of the tire is going 60 miles an hour. Right? The instantaneous speed of the bottom point, what do you think the instantaneous speed of the bottom point is? It's like 0. And then what do you think the instantaneous speed of the top point is? It's like 120. It's like 120 miles an hour. Right? So funny tire physics. But here, if you backdraw this, wouldn't it go to exactly the hinges? Okay. And then now there would be a net force to the right, so maybe it would be pulled to the right, but no torque. So without spinning, would you guys like to see this slide across the page without spinning? Do you think that's possible? Can I really get this thing to move without spinning? Okay. Let's see. Okay. I've got a sticky note for the camera, so this is actually not spinning. Okay. Let's see if I can get that angle. Right there, right there. See it sliding without spinning? Even though it's a rolling object, but it's actually not rolling. It's so weird. This turntable wants to spin. Yeah. Okay, so let's go back to that problem that I left you guys with at the end of yesterday that almost set up and almost solved and in that time, which is, remember how torque is, okay, obviously it's R cross F, so R times F times just the perpendicular components, but it's also equal to I times alpha, right? That's analogous to Newton's second law of motion. Okay? And I want to solve a quick problem with you guys with this. So suppose you had some solid cylinder. Hey, maybe kind of like this turntable. Like this turntable is basically a solid cylinder, or pretty close to that. You could approximate it with that. Okay? And maybe you know some things about the solid cylinder. Maybe you know its mass. I'm going to just make up a value. Let's call it like 3 kilograms, okay? Which is way heavier than this one is, but let's say you know its radial size maybe I'll just try to stick to integer values. So I'm going to say maybe it has a radius of 5 meters. Okay. And I've got some string wound, string going round. Okay. I'm going to pull with a force of, I don't know, maybe 15 newtons. Okay. See how this plays out, something like that. I might have a question, like maybe if I pull for some amount of time, how fast is it spinning? Like that'd probably be a pretty good question, right? I bet that could be like an FRQ, pretty good one. Okay. Actually, I'm not gonna quite solve that, but I'll solve like halfway up to that point. Because to get there, maybe, guys see this alpha? Isn't this alpha going to connect this dynamic motion, and this is all dynamics here, back to that kinematic type motion, and then I could solve for like how fast is it spinning after some time interval? Okay. So maybe I'll take you guys up to that point. Okay. So what did I here? Oh, well, R, I know that. Okay. F, I know that. If it's a string around the cylinder, then it's always going to be at right angles, so that takes care of the cross product. You just multiply the magnitudes. Okay. What about this I? Well, I know the mass of the cylinder is 3 kilograms. Okay. This is where you open a textbook and say, well, what's the associated rotational inertia for some particular shape? Okay. So for AP, it's in your college physics textbook on page 257, here's solid cylinder. Okay. It says, here's a solid cylinder. It says 1/2 mr squared. That's sort of like the aggregate effect of having some mass that's closer to the center. And for honors, since I'm making an all video for everybody, they got a table that looks like this, and 1/2 mr squared. So same thing, right? The different tables, same result. Okay. So I can say then that actually let me take this down here. Okay. So R times F. So R of R F, and they're already at 90 degrees to each other, is equal to. Now instead of I, I'm going to replace that with 1/2 mr squared, because this is the I value for a solid cylinder. Okay. You find that in textbook, but this is a really classic shape to be rotating, so it might not be a bad idea to memorize that for solid cylinders, just 1/2 mr squared. Times, of course, alpha. And we're solving for alpha. What's the rate that it's speeding up spinning, so that you can therefore do a bunch of kinematic work on that later. Okay. So looks like one of the r's is going to cancel. And if you want to isolate alpha in terms of variables, that'd be cross multiply the 2, divide down the mr, and alpha is going to be 2f on mr. Okay. Specifically for a solid cylinder. Now, of course, if it's another shape, it's not going to be exactly this expression. It might look kind of similar, but kind of that, right? Okay. Like, I bet if it was just a ring, this half would never have been there, so this 2 is not going to be there. For a ring, it might be just f over mr, something like that. Okay. Let's plug in the values. So I said a force of 15 newtons, so 15 Newton force. And I said a mass of 3 kilograms, so 3 kilograms, and a radial size of 5 meters. And looks like it's going to be 2, it's going to be the number on the calculator screen. But what's the unit? 2 what?
Radians per second squared.
Radians per second squared, exactly. Because that's how you measure alpha, like the rate something's speeding up spinning. Okay? 2 radians per second squared. Okay? Or how about this? What's newtons divided by kilogram meters? That leaves you with 1/second squared. Radians is one of those like hidden type variables, or units, I should say. Okay. Now, this is where you could say, well, once we figure out alpha, that's the rate it's speeding up spinning. You can go back to this and say, now I know alpha. Say it started from rest, I pulled for so many seconds. I know, how many radians it's gone through, or down the second equation, how fast it's sped up to. Okay? Is it? Right, so yeah, that could totally be an AP question right there. All right. You guys ready for this thing hanging from my ceiling? I'll wait for that one. So, all right. You guys see hanging from my ceiling is a meter stick with a weight hanging on it. I draw this Right, meter stick, a couple of strings, something like this. And there's a weight hanging right at the center. It's a 1 kilogram mass that weighs how many newtons about? 1 kilogram mass weighs about, yeah, about 10 newtons. It's like 9.8, but we'll call it about 10. Now the meter stick itself weighs a little over a newton, maybe I'll round that to a newton. And even though its weight and its mass and its weight is distributed over an entire, of course, the length of the meter stick, it's okay. It actually is perfectly okay for us to treat its mass and its weight acting at its own center mass at the 50 centimeter arc 2. And so that gives you a total value of 11 newtons. I'm rounding a little bit, but it's basically 11 newtons. So 10 from the weight and 1 from the meter stick. Right, so the fact that it's dead in the center, could you guys tell me exactly what these two string forces have to be? What do they have to be? Yeah, 5.5 newtons each. 5.5 newtons, 5.5 newtons. There's a specific reason I haven't written any equations yet, because I want you to see that like, you could obviously sort of figure that out. Okay, walk over here, let's check it in real life. 5.5, 5.5. Great, all fine and good. Okay. Okay, now let's think, what would the guiding physics principles behind this be? Well, this is a question of equilibrium. Equilibrium. Okay. Tell you what, before I tell you what that is, right, I want you guys to stew over this question a little bit. What if I take this weight now and I shift it, let's say to the right, let's say closer to the string. Okay. What's going to happen to the force in this string? It would go up. What's going to happen to the force in this string on the left? They would go down? What do you think these two string forces would add up to? Still add up to 11? This is what you guys just told me. You guys just told me that the sum of the forces, in this case in the y direction, is equal to 0 newtons. Isn't that what you guys just said? You just said that, right? And that is one of the conditions for equilibrium that you guys have known for a while. But you know what? There's actually another condition that I haven't told you yet that I'm about to. Okay? But I want to tell you guys a story for a day that's going to lead to this. And that's, you guys know Paul Hewitt, the guy with all the fun demos, right? College. Okay? He actually had a late start in life. He got out of high school, worked a bunch of odd jobs. He was a boxer at one point. People punched him in the head. He was a sign painter. And he would walk around on the scaffolding that was held up by these ropes. He would walk with another painter. And they noticed, like, say you had one guy over here, another guy started walking towards that way. If they were sort of like twanging these ropes, like boing, boing, they would like go up and pitch, like boing, 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 boing. Think, I see the tension's going up, but I wonder exactly what is this relationship. They were looking at like this, basically this problem right here, trying to figure out what's the relationship exactly. And Paul Hewitt said, you know what, I'm going to go back to college and I'm going to figure out this problem. And that's why we have all these Paul Hewitt demos today, because of this question right here. Okay. So here's the other condition, is that the sum of the torque is also equal to 0. Well, it'd be Newton meters. Okay. Because if you didn't have that condition, otherwise it would be ambiguous as to exactly what these two forces are. Now, you guys told me they have to add up to 11 newtons. That's true. Right? But say if I park this at some location, let's say like 3/4 the way over. Okay? Exactly what would the numbers be? That top condition by itself, they add up to 11, but exactly what are they? Well, there are a lot of possibilities. Maybe it's like 10 and 1, maybe it's 9 and 2, maybe it's 8 and 3. What is it? And this other condition, this will let you get it. So let me draw that situation, because that's what I'm going to do. I'm going to slide that over, and then we'll figure it out. We'll do the math on it, and then we'll go do the actual science, the empirical science, and see how well it matches up. And so get this meter stick back. Okay. Of course, this is 100 centimeters long. Okay. Here's the halfway point. Now, remember the meter stick itself has a little bit of mass, a little bit of weight, okay? And even though it's distributed over the entire thing, I'm going to assume that it's all acting at the center mass, which is perfectly fine mathematically to do. So that's about 8 Newton by itself. Okay? And I'm going to take that 1 kilogram mass, which weighs about 10 newtons. I'm going to put that over here at the 3/4 to the right mark. So call this guy 10 newtons of downforce. Like that. Okay. Now, you guys already told me that the string on the right better be pretty high tension, and the string on the left is probably going to be pretty small tension. Okay. We don't know what those values are, F right and F left, but you guys do know that they have to add up to 11 newtons because of this condition here. Right? But what exactly are they? Well, that's where this torque is going to come into play. Okay. Now, I know for the door example, let's see, where's my door notes I just had? I know for this door, it's like R cross F, right? R cross F, right? And that's relative to these hinges over here. But where are the hinges on, say, like this problem? Right? Well, you guys want to know something really crazy? Right? Is that you are actually allowed to define the pivot point, say like the hinges, wherever you want, and the torque will always sum to 0, right? So, no, there are some places that are better than other places for solving problems. Like, how about this? If I pick this point on the far left as my pivot point, as my pivot point, okay, there's actually an advantage in doing that, and that's that one of the unknown values, one of the unknown forces, if I walk up to that door and I start pushing on the hinges, is that going to rotate the door? No. So does this force acting at the pivot point cause any torque without that pivot point? No. So it's like it zeroes out in terms of the torque. Is that okay? So that takes 2 unknowns and it just narrows it down to 1. Is that right? So there's an advantage of doing that. But from a broad physics point of view, there's no one point that has to be the pivot point. I could pick the right end. Right? I could have picked this point. I could have picked this point. I could have picked this arbitrary point right here. I could have even picked this point. Like you could pick a point off the meter stick. Some of the torque about it also still works out. You guys can test the notes out later, see if this works. But it will. So let's see. I'm gonna say you guys know that this distance here is 50 centimeters. So you got 50 centimeters. You guys, here's what I'm going to do. I'm gonna park this guy over here at 75 centimeters. So this is going to be 75 centimeters. Okay. And then, of course, the high tension string on the right side is all the way over at 100 centimeters. Okay. You see that? Okay. Relative to this arbitrary pivot point. Okay. Although it's not completely arbitrary. I picked it so that the torque from the left force would zero out. That's why I picked that point. Okay. Right, so we're really going to solve for this, and then we'll figure out F left later. Okay, so imagine that we're looking down on a door, and I see the hinges on the left side, and I got like 3 different people pushing on the door. I got 2 people pushing this way, and 1 person pushing that way, trying to make the door rotate different ways. Of course, it's all going to zero out because it's in equilibrium. Okay? But see how this torque here is like clockwise, okay? And this is a huge clockwise torque because it's not only 10 times the force of this one, but it's also further out, so it's going to be like more than 10 times the torque. Okay. And then I've got this big old force, this big force on the right side, that's a really long way away, it's 100 centimeters away, that better be holding those 2 in check. Okay. Like this kind of torque. Okay. Now I'm drawing those like curvy lines to represent like clockwise, counterclockwise. But see how this big counterclockwise and these 2 smaller clockwise ones better zero out? Hey, that's this bottom condition right here. Okay, is that there? There you go. All right, so also torque is a vector. I forget if I mentioned that, but torque is a vector quantity. So it could be positive or negative. Usually how you consider these is that clockwise is negative and counterclockwise is positive. Right? In a few minutes, I'll give you guys a different perspective on torque that AP doesn't really stress about, but you might see in the future, okay, which is something called the right-hand rule. So R cross F, you guys remember how torque is equal to R cross F? Okay. If you point your fingers in the direction of the R radial distance, starting from the pivot point, okay, and then curl your fingers in the direction of the force, like R cross F, okay, then your thumb will, for anything that's clockwise, will point into the page. You can think of that like a torque in the z-axis, like into the page would be negative, like down. Okay, same story for this guy, R cross F. Okay. But this string on the right side, upward tension, upward force, R cross F. See how your thumb would point out of the page? So that like a positive torque. Okay. So AP is never going to ask about that, but might say in the future. It's what are these values? What is 50 centimeters times 1 Newton? Wouldn't that be 50 Newton centimeters? Okay. Remember, unit for torque is always Newton meters, Newton centimeters. You might be tempted to call that joules, but torque is never called joules. It's always like Newton meters, in this case, Newton centimeters. Oh, and it's negative because clockwise. Then I've got, at 75 centimeters, I've got 10 newtons. So isn't that negative 750 Newton centimeters? Wouldn't that be true? That's all right, right? Okay. And then finally, the far end, there's, well, we don't know what force that is. But I bet you guys can look at these numbers in this condition, and you guys can tell me exactly how many Newton meters of torque this has to be. And what does it have to be?
125.
What's going to zero out with, guys, what's negative 50 plus negative 750? Negative 800. So I've got 800 units of torque saying let's go clockwise. Do you think that this guy holding it in check better be 800 Newton centimeters of torque holding counterclockwise? Okay. This number has to be 800 Newton centimeters, okay, because of this condition. Okay. Oh, also, you know the location it's at. So guys, here's 800 Newton centimeters, positive. Here's 100 centimeters radial distance. So what force would be applied to make that happen? You see 8 newtons? You guys see that this has to be 8 newtons of force? Right? 8 newtons. Because that would provide the necessary torque. Is that? Right? And if, okay, questions right now? And if that's 8 newtons up, then what does the left force have to be? 3. Yeah, because 8 plus 3 newtons, would be 11 newtons up. And I've got 1 plus 10 newtons pulling down. Ah, you see 11 up, 11 down, it balances out. Okay, so we just solved that problem. This string better be 3 newtons, and this better be 8 newtons. Right? Is it? Guys ready to do the actual science on this and see how well this actually works out? Right. So walk over here. I'm going to take this kilogram mass, slide it over to the 75 centimeter mark. Try that right there. And you guys can watch this too as you're walking by to go to lunch. And on this spring scale, 8 newtons. In this spring scale, 3 newtons. Boom, exactly. Got it. It works exactly. Guys go there? All right, so some other things about torque. I did mention the right hand rule, so I'm going to show you guys an animation about that. But let me draw a wrench because I feel bad if I didn't draw a wrench. This is another classic torque example. Okay. Wrench. Let's say there's like some rusty bolt or something, right? You're trying to like loosen this thing. Okay. How can you maximize your chance of doing it? Let's say it's really rusty. Okay. Well, I bet you'd want to apply a force. You'd want to maximize the force that you're pushing with, obviously. Okay. But wouldn't you also want to apply that force as close to the end of this wrench as you could? So like maximize this radial distance. Because if you did like at the halfway mark, but you kind of like trying to put a doorknob in the middle of the door, you'd be only getting half the torque. So remember, torque is R cross F. Okay. But one more detail. Not only maximize the force, maximize the radial distance, but you want to have that have these at right angles to each other. So have that angle as close to 90 degrees as possible. You guys remember this is R times F times sine theta. Here's your theta. Right? Okay. And then right hand rule says that R cross F. See my thumb's pointing out of the page versus, so that would be like a positive torque the way I've drawn it. Okay. Now, AP doesn't care about positive and negative torque. AP always couches it in terms of counterclockwise and clockwise. So this would be counterclockwise. You guys see counterclockwise? And this would be. Okay. But the reason I bring this up is because I want you guys a really cool trick with torque. Here's where I'm going to switch my screen over. So present screen to share. Right. So we're looking at this animation. Right. So you guys see that dark red vector is R, like radial size. The dark blue vector represents a force, like an applied force. Okay. And then, do you guys see like a light blue vector that's pointing along the z-axis? I mean, we got this xy plane that the other vector's on, but we got the z-axis that's showing like torque, right? Now, I like to think of torque as like a clockwise, counterclockwise concept on an xy plane, but you could use right-hand rule and say, direction of your thumb. You could treat torque as a single arrow vector, right? You could think of it like that, and they could add or subtract each other like a quantity. Right? So that's a nice trick. Now, why is this really, really useful? Right, you guys ready to expand your minds into something really tricky? Right. What's going on here? That's not what I want. Here, I want this one. Cross product organic chemistry. Ah, there we go. Adds. Okay, yeah. Bam, skip. All right, so how many guys have know about matrices? Matrices. You guys ever done matrices in math class? Okay, so some of you guys have. Okay, great. It's been kind of spotty. Some of you guys have had teachers who have, some haven't. Now, matrices are one way that you can solve math problems, say alternate to, well, some other methods. You can actually use them alternate to substitution or elimination to solve system of equations. But I'm going to show you guys how to solve like really tricky cross products. Right? So see, we've got vector A and vector B. This represent vectors. Now I, J, and K just refer to X, Y, and Z directions. Right? And oh look, he's doing a cross product, A cross B. Right? So let me copy that down exactly. So I want to turn this into an R cross F torque example. So A is equal to 3I plus 5J minus 7K. And B is equal to 2I minus 6J plus 4K. Right? And so switch back over. Right. Okay, so I copied it down exactly, except that I changed one detail. Instead of vector A and vector B, I changed that to R and F because we're going to do a torque application of this. But mathematically, it's the same thing as what he's going to show in the video. Okay. So let's get some axes going. Okay. Now you have to think in 3 dimensions for this. Think in 3 dimensions. So I'll have an x-axis, a y-axis, and a z-axis. And just imagine x, y, and z. Right? And I'm going to take that wrench example that I just showed you. Now this is in 2 dimensions, right? But we're going to take this into 3 dimensions, and that's another advantage of like matrix math is you can go into like as many dimensions as you want. So we're just doing 3 dimensions here. Right? And R 3, that's an x value of 3, so a y value of 5. And a z value of -7. Right? And that's a radial value. So think of this like the length of the wrench. So maybe like I have a wrench that is 3 units over, 7 units up, and then 3 over 5 up on the y, and then 7 down on the z. So when I take it to like right about here, what if there was a bolt right there, and you had a wrench that went to this origin point? So gotta think in 3 dimensions. So we've got this 3-dimensional situation going on, and you want to apply a force. Here's your force. It's 2 in the x direction, -6 in the y direction, and 4 in the z direction. Okay, so going from here, see, 2, -6 is right there, up 4, right about here. Okay, so here's the force that you're applying. In 3 dimensions, right? So it's sort of coming out of the page a little bit, this force. Right? What is the torque associated with that crazy example? Right? What is the torque? Okay. Yeah, you guys see the concept? What's going on? Okay. All right, so I'm going to flip back over. See, present my screen again. Okay. Now, If you remember this from a math class, then awesome, you can do this. And if not, then this might be something you want to check up on yourself. Okay? So you can solve this with a determinant, and then you go through this whole video just showing how to solve that. Okay? And then at the end, it's, you guys see that in that red box? That is, well, for our example, that would be what the torque would be, the torque. 26 in the x, 19 in the y, and negative 18 in the z direction. Okay? But remember that that is represented like an arrow vector version of this, which is kind of like this light blue vector along the z direction. So then you can go back and say, well, on an xy plane that's orthogonal to that, then get some kind of clockwise or counterclockwise equivalent of that. Okay, so I'm showing you guys all this only because I want you to be familiar with it, know that that's there, that's where you can go with this physics, but that is beyond the scope of anything we're really going to do in this class. Okay? But that is there, that's how that works. Okay? Right, next concept. Let's go to rotational kinetic energy. Rotational kinetic energy. Okay. Now, you guys know kinetic energy. Okay. Translational kinetic energy, I'll call it K translational. That's your 1/2 mv squared, the energy of motion. Something's in motion, how much energy associated with that? 1/2 mv squared. Okay. But there also is some energy associated with something like rotating, okay? And it would be kinetic energy. I mean, if I rotate this platform, then you say, well, there's a lot of 1/2 mv squared going on, but it's a different v for like different points on this turntable. Okay? Like this point has 1/2 mv squared, this point, this point, this point. If I broke this into like a billion different points, I could sum up all the 1/2 mv squared. Okay? But they all have a different v. But you know what? They all have the same omega. They all have the same turns per time, same radians per second. Okay? Which might be a hint as to what K rotational is going to be. The rotational kinetic energy. Okay? And you know what? All you have to do is pop in the rotational equivalents of these linear motion variables. So it ends up being this, 1/2 I omega squared, just like that. Okay. Okay, so what can you do with this? What sort of an application? Maybe you have an incline. I'm actually going to have this incline go up the other side too. Okay. I'm going to have a race between two objects. Goes off the page a little bit. Okay. I'm going to fix to two hula hoops. So hula hoop, a couple of meter sticks. And on these meter sticks, I'm going to tape some masses. On this one on the left, I'm going to tape these pretty close to the center. On the one on the right, I'm going to tape these pretty close to the ends. Hey, these are the 2 meter sticks I just passed around in class. You guys got your hands on? You guys felt those? Okay. Which one of these has a lot of rotational inertia? Yeah, this guy right here, right? So which one's going to win? Suppose there's a race to the bottom. Got a finish line down here. Which one wins the race to this finish line at the bottom? Yeah, how about this guy? The one that has a little tiny rotational inertia. Here's this guy's rotational inertia. Here's this guy's rotational inertia. Okay. So, yeah, the guy with almost no rotational inertia gets going in a hurry. Zip down to the bottom. Right? It's going to win the race. Okay. But it's also easy to stop once it's down there. You just whatever, stop. Right? Now this guy, it takes forever to get going. Like, please start rolling. Okay? But once it is rolling, also really hard to stop. Right? That's what inertia is. Okay? So here's what. I forgot to mention a little important detail too, is that you do need static friction to induce rolling. If you had no static friction, these wouldn't actually roll. These would it would look really weird if it's like frictionless. It would actually like not roll, right? So you do need static friction. And if there's no sliding friction, let's say like you might actually not be losing energy out of the system. Here's what this motion would look like. Here's the little guy, the little I guy. Right? Zoom, 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 zoom. Here's the large inertia guy. And if there's no energy loss from the system, they could do that for like 1,000 years. It's like zoom, zoom, zoom. Right? Like that? Is it? Hey, I'm going to take this example And let's expand this a bit. Let's do let's get ourselves a big old mega race going. Different early objects. Okay. Let's go a bowling ball. That's to say maybe a solid sphere. Okay. Let's go a solid cylinder. Let's go a basketball. And a ring. I wonder who's going to win the race to the bottom of that incline. Give you guys a hint. The mass of each of these things is going to cancel out. The mass itself ends up not being important, but the distribution of the mass actually does matter. Okay? Oh, so this is a rotational inertia connection, isn't it? So if you look at the table in the book, you'll see that for a ring, well, here, I'll do it this way. I equals, for the ring, it's just pure mr squared, because every single point is mr squared, and then they're all equidistant from the center. Yeah. The basketball is 2/3 mr squared. It's pretty big because all its mass is at the surface, so it's kind of like the ring, and so it's all pretty spread far out. Okay. Now the cylinder, now it's getting distributed closer to the center. It ends up being half mr squared. These are all textbook values. Just look at that table in the book. Okay. And then the bowling ball is distributed closest to the center, and ends up being 2/5 mr squared. So you guys see I put them in rank order.
No. It was rigged from the start.
Yeah. So we got 100%, got 67%, 50%, and 40% of mr squared. Right. So who wins that race? The bowling ball. The bowling ball wins the race, and the bowling ball is also moving the fastest at the bottom, isn't it? Okay. Yeah. So what's the conservation of energy equation setup going to look like for something like this? Well, I can say sum of energy at the top of the hill is equal to the sum of energy at the bottom of the hill, initial to the final point. And at the top of the hill, let's say just pick one of these, like the basketball, right? Wouldn't it be all mgh? They start from rest, it's just mgh. Right? That's your starting energy. Right? At the bottom of the hill, you actually have two different kinds of energy. Okay? There's translational kinetic energy, because there could be like a guy with a radar gun here. Okay? Here's this radar gun. Okay? Stand here. Maybe on this grassy knoll. Okay? And he's getting the translational speed, like how fast, like meters per second with this radar gun. So that's something to do with 1/2 mv squared, right? Okay. But there's also some energy that goes into making these things roll, like rotate, right? And wouldn't that be your 1/2 I omega squared? That be true? Right, guess so. Right, so that's the general setup. Right. Now we'll probably solve this or something very similar to this in the future, because I really like this question. Right. But today I just want to plant this idea and have you guys see the big picture of this. Right. But it will give you guys a little bit of headway of how this is going to sort of go, which is that, see this I? This I is different, obviously, for each of these, right? But it's proportional to mr squared, isn't it? Proportional to mr squared. Right? And this omega, well, isn't that just v over r, right? And why am I saying that? Because this v and this v are the same thing. And this mass and this mass, and this mass for that matter, are the same thing. You guys see mass is going to cancel out, right? Okay. So it's not the mass of these things that matters, it's the distribution of masses. Okay? So that's how you can start to consolidate these variables and actually solve for the speed of the bottom. All right, guys get that? All right. Right, finally, last thing we'll do is I'm going to flip over and show you guys part of a Mark Rober video where he takes this type physics and applies it to a Pinewood Derby car. So stop the recording right here.